Hi, in this video, I'm going to continue on industrial chemistry, and in this part, we will be focusing on the Arrhenius equation. Now, Arrhenius equation, as shown here, is used for two purposes. One, it is used to show the relationship between the rate constant and the temperature. As you know that the rate constant is related to how fast the reaction proceeds, and you can tell temperature definitely affects the rate. And this equation is able to show you such a relationship. And secondly, which is more importantly, this Arrhenius equation allows us to calculate the active fission energy for a given reaction, provided that we know the rate constant corresponding to a temperature. Okay? Now, let's break it down to you how this equation works. First of all, K is the rate constant. Again, the larger the rate constant, the faster the reaction. A is a constant. We call it frequency factor or pre-exponential factor or Arrhenius factor. We will talk about this factor later. EA stands for active fission energy. R stands for ideal gas constant, which is another constant, and it is always 8.31. And T is temperature, but bear in mind, it must be in Kelvin. It must be in Kelvin. Okay? Now, first of all, let me explain to you how this equation is valid. Now think about it. Let's just say I have a reaction that is very, very fast. So you can tell the rate constant K should be large. Now when K is large, then the term on the right hand side, now A is a constant, we can forget about it. The whole term, E to the power negative EA over RT, this whole term will be large. Okay? Now think about it. If this term has to be large, then the index, since it is negative, so the index term should be of a small magnitude. Okay? So this negative EA over RT should be small in magnitude, that means large in value. So if this one is large, so that means less negative, that means EA over RT should be small. Okay? Do you agree? Let's just say you have 10 to the power negative 10. Okay? Actually, the number is very small, 10 to the power negative 10. But you notice that the magnitude of the number in the index 10 is quite large. Okay? So similarly, here, if you have a term that is large, that means the negative index should be less negative. So perhaps it is like to the power negative 2. So to the power negative 2 is definitely larger than to the power negative 10, right? So that's why we can conclude that this term, EA over RT, is a small number. Okay? When EA over RT is small, what does it tell you? It tells you that EA must be small and T should be large. Okay? EA should be small, T should be large. Okay? Because think about it, you have a smaller numerator and a larger denominator. R is a constant of which we can't change it. Okay? Now, look at the relationship between the rate constant K, the EA, and T. This is consistent of what we have discussed before. Because when the active fission energy is low, that means there will be a greater proportion of particles having energy equal or greater than the active fission energy. Therefore, the reaction should be proceeding very fast. Therefore, the K is large. So that makes sense. Also, when temperature is high, then the reaction is faster. Okay, you can explain it using collision theory, you can explain it using active fission energy, using the Boltzmann distribution curve. So you see, this equation is valid in terms of the relationship between active fission energy, temperature, the rate constant. Okay? Now, very often, we don't use this equation in exponential form. We find it not very convenient, especially the E here. Now, by the way, for some of you who are not familiar with exponential, if you are asked, let's just say you are given with all these numbers on the right hand side and you are asked to calculate K, then, well, in order to type this function, exponential function, on your calculator, you are going to press Shift Ln. By pressing Shift Ln, you will have this E, okay? And this E is the exponential there, okay? Then you can just type the numbers, type the EA, R, T inside the bracket here, also multiply by the A if it is given, then you can find K, all right? Now, this equation, you can use it like this, but very often we will take a natural log on both sides. We'll take the natural log on both sides. Now, when we take the natural log on both sides, then this equation will become this. ln(a) equals to ln(a) plus EA over RT. Okay? Now, I will explain to you why it is better to be written in this way later, especially when we talk about the graphical method. Okay? And in DSE, sometimes this equation is given, sometimes it is not. So therefore, you need to either memorize this or you either memorize this. Okay? Now, let's have a look at down here. Basically, something that I have mentioned. So, you know that the rate of reaction depends on the activation energy as well as the collision frequency. Okay? And this term, e to the power negative EA over RT, actually accounts for the effect of activation energy and the temperature. So this one, I have talked about it, okay, how this term is related to these two terms. Okay? Now, but what about collision frequency? Collision frequency. Now, the collision frequency is actually accounted by the term A here. Now this one is out of syllabus, but I will explain a little bit. So down here, whether or not a collision is successful, or whether or not a successful collision is easy, depends on several factors. So it depends on some intrinsic property of the reactants, which is including shape, charges, and size. Now think about it. Molecules with large size is easy to collide on one another, right? And the shape as well. If you have learned biology, you learn about enzyme and substrate. You know that when the reaction takes place, the substrate must be bind on the active site, okay? Well, whether or not the enzyme-substrate reaction is fast or not actually depends on whether the active site is easy to bind with the substrate. And whether or not it is easy to bind on substrate depends on the shape of the active site, whether or not it is well exposed or whether it is covered by a lot of bulky groups. Also related to the charges, right? Because very often the substrate and the active sites, they are oppositely charged, and therefore they can be attracted easily. And of course it depends on the differential charges of the active sites as well as the substrate, so it also kind of determine whether they can bind onto each other easy or not. So all of these are intrinsic properties, okay, of the reactants. And the second one is the order of reaction. Order of reaction. Do you remember that I have mentioned that a third order reaction is very rare? Okay. The reason is because when we have a higher order reaction, like third order, fourth order, fifth order, we are talking about that rate determining step involving many particles colliding on each other at the same time with sufficient energy and as well as heating with the proper orientation. Now, it is difficult for 2 particles. It has to be much more difficult for 3 particles, 4 particles, etc. So here, the chances of having 2 molecules colliding together is much higher than having 3 molecules colliding to each other, as well as having sufficient energy and proper orientation. So that's why the order of reaction is also affecting the rate of reaction, or affecting the rate constant, okay? And all of these intrinsic properties, orders of reactions, are actually very difficult to calculate. And therefore, this term, Arrhenius factor or frequency factor, will be accounting for all these factors, okay? Of course, there will be separate calculation, but that would be too difficult for DSE level, okay? And these factors, they are independent to temperature, because like I said, it is all intrinsic property. The size, the charge, the shape of the reactant will not be affected by the temperature. Okay? So this is how it works. Now let's look at the practice question. Basically, let you to be more familiar with the Arrhenius equation. So pause the video, attempt the question, resume the video, and check the answers. Okay, now for a given chemical reaction at 25 degrees Celsius, the rate constant is given, and the Arrhenius constant is also given. Calculate the EA, right? So, well, we can use the Arrhenius equation, K equals to A times E to the power EA over RT, okay? So we just sub in all those numbers that we have.
K will be 2 times 10 to the power 85. A is given as 5.19 times 10 to the power 13. Exponential negative EA, this is what we're looking for. R is 8.31.
T, is it 25? No, it should be 25 plus 273, because remember the temperature, we use Kelvin temperature, okay? Then basically we just tap our calculator to find the EA, okay? So to do that, we can first divide both sides by the Arrhenius factor here. So we have 2 times 10 to the power negative 5 divided by 5.19 times 10 to the power 13. Okay? And then we want to get rid of the E, so we take natural log on both sides. Just in case you can't follow. Now we should have this one on the left, and still with the E terms here. Okay? And then we take the natural log on both sides. So natural log answer, because by taking natural log on both sides, we can cancel out the E. Okay? So we natural log the terms on the left. We have negative 42.4 equals to negative EA over 8.31 times 298. Okay? Now this one should be easy to tackle. So the negative are all cancelled out. And then it multiplies 8.31 multiplies 298. So this EA would be 104,998.8047. Now in here, the active fission energy is in joule per mole. Okay? This is because the ideal gas constant is using joule. Okay? But usually for active fission energy, we use kilojoule per mole. So therefore, we should make it 105 kilojoule per mole. Okay? Alright. Now remember, active fission energy must be a positive number. So if you get something negative, probably you haven't dealt with the sign, the positive and negative signs properly. Okay? Now what is the order of the reaction? So actually, the order is kind of implied by the unit of the rate constant. So the rate constant unit is s to the power negative 1. This implies first order reaction. Okay, so it's like rate equals to K times A to the power 1. Okay. Next page. The next page is very important. Graphical representation of Arrhenius equation. So here, this is what we did earlier. We take natural log on both sides of the equation, and then we get something like this. Okay. Now this is coming from what I have here, because after you get this one, you rearrange the terms. Basically, you have you take EA over R out, so you have EA over R, you take it out, so 1 over T, and then plus natural log A. So simply rearranging the terms, then it is in the form of, y equals to mx plus c, isn't it? This is exactly what we have in here. Alright? Y equals to mx plus c. Okay? So basically, we're using this one as well as this one. We plot the graph here. Okay, natural log k as the y-axis, and then down here we have 1 over t as the x-axis. Okay, can you see it? This one and this one. Okay. Then we can plot a straight line graph, right? So temperature. Well, we can definitely vary the temperatures when we do experiment. We can use different temperature for different reaction trials. For K is the rate constant, and rate constant is directly proportional to the rate. So we can make use of different experimental technique that we have learned in the core topic to find some terms to represent K. So very often we use the 1 over t. The t is a small t, the time, to represent the rate and therefore to represent the K, right? Never mind, all you have to know at this moment is that we can experimentally determine, of course, the temperature and the rate constant, and then using the experimental data, we can plot a graph of natural log K against 1 over t. Then after we form this straight line, then the slope of this straight line will be negative EA over R. Knowing that R is our ideal gas constant, then we can calculate the activation energy for a chemical reaction. So this is important because this allows us to experimentally determine the activation energy of a given chemical reaction. Okay. Also notice that by extending the curve backwards, where it meets the y-axis, then we can find the y-intercept and the y-intercept, and the y-intercept is the Arrhenius factor. Okay. So on the right hand side, this shows you how it works. Now we have this reaction. We have cyclopropane forming propene. All right, and we make 4 trials at different temperature, and we also have the rate constant K determined. Okay. Now using these data, we are going to modify this data as shown below. First of all, the temperature, they are in degrees Celsius, then we need to convert it into Kelvin temperature, and then we also have to take the reciprocal of the temperature. So 1 over T, then we register these data. From the rate constant, we take natural log, then we register these numbers. Okay? So we are using these two numbers, these two data, to plot a graph. Okay? After plotting a graph, which is like this, then we find the slope. The slope down here is determined as negative 3.27 times 10 to the power 4. Okay? So solving this simple equation, we get EA equals to 273 kilojoule per mole. Okay, so this is how we determine the activation energy by graphical method. Also, we can find the y-intercept, which allow us to determine the Arrhenius factor. Okay, Arrhenius factor, the unit is s to the power -1. Okay, but of course, in reality, plotting this graph requires some tedious work. So in the DSE exam, we have no question asking you to plot this graph. Before in A level, there was question asking you to plot a graph, and graph like this will be like 5 marks, okay? Because you have to modify the data, and it also takes quite a lot of time to plot a graph, okay? But make sure you know how to interpret graphs like this, okay? Now at the back here, we have a practice question. So I would like you to try working on this question. Okay, and after you have done it, resume the video. Okay. Okay, so let's check the answers. Now, basically, you're given with some temperature and rate constant. You need to plot a suitable graph to determine the active fission energy of this reaction. So all these data must be modified. So I will do it here. So temperature in Kelvin, but what we want is 1 over T. We want 1 over T. Okay? So 1 over T, you do it one by one. Okay? Now, you do the natural log K on the right hand side here. Okay? Then we need to plot a graph of natural log K against 1 over T. Right? Of course, make sure you know the equation natural log K equals to this one. Okay? So we start out with y-axis. Okay, so once you have plotted the graph, you can find the slope of the graph here. So slope equals to, now of course you can choose any 2 points. Okay, and in this case, by looking at the point that I have plotted, perhaps I will use the first data and the last data to calculate the slope. So we have y here. Okay, and knowing that, since slope equals to negative EA over R, so we have negative 1447.477 equals to negative EA over 8.31. So EA is
this term multiplied by 81 multiplied by 8.31. So we have this one and divided by 1000. So we have 12.0
kilojoule per mole. Okay, so this is how it works. So you see, there are actually a lot of work to be done to graphically determine the EA. Okay. So like I said, DSE, they won't ask you a question like this, but I would like you to at least try once yourself to see how it works. Okay. Okay. Now let's look at part B. Now part B. State the color change occurs when the reaction proceeds. Now we have to check the equation. So you notice that among all these chemical species, only one chemical species has a color, which is NO2. What is the color of NO2? Well, NO2 is reddish brown in color. So therefore, state the color change occurs. You can say the color changes from colorless to reddish brown. Okay? From colorless to reddish brown. Okay, 2. Suggest how you can determine the time when a significant color change has occurred. So you can use colorimeter to measure the absorbance of the reaction mixture. Okay? Or you can use the traditional method using a cross, and you put the cross underneath the container, and you want to see how long it takes for the cross to be masked by the gaseous mixture. Okay? Now, 3. State the relationship between the time taken for a significant color change and the rate constant. So, the rate constant, of course, is inversely proportional to the time it takes. So, inversely proportional. Because the shorter the time it takes to reach a significant color change, you know, a significant color change basically implies a certain amount of NO2 product being formed. So if it takes a shorter time to reach a certain quantity of product, that means the reaction should be fast, and therefore the rate constant should be large. So the shorter the time it is, if this one is small, then K will be large. Okay? So this is how it works. Now, so this practice question shows you how you can graphically determine the activation energy. Okay? Now, on the right hand side here, we are going to discuss a non-graphical method. Now, for the non-graphical method, to be honest, is also frequently asked. Like I said, the question cannot ask you to sketch a graph or plot a graph because it's so tedious and time-consuming. Therefore, they will opt to give you questions related to non-graphical methods. Now, you notice that this one is the rearranged exponential expression of Arrhenius equation, y equals to mx plus c. Now, using a graphical method, you're looking for the slope, isn't it? But you notice that a slope is essentially made by 2 points only. So if we have 2 data points on a graph, then we can determine the slope. Or in other words, we can simply make use of the data from that 2 data points to calculate the slope without actually plotting a graph. So this is actually how it works. We make use of two sets of data, and we find out the slope. And we find out the slope using the method of simultaneous equation. Okay? So if you have 2 temperatures, T1, T2, and the corresponding rate constant K1, K2, then we form 2 equations, and then we can combine the 2 equations. We have 2 minus 1, 2 minus 1. When you do 2 minus 1, you can get rid of the natural log A, and then we have something like this. Okay? And then after rearranging the terms, we have this equation. Okay? Now when natural log minus another natural log, that is equivalent to natural log, okay, K2 over K1. Okay? And this one, we group the EA together, and then we put 1 over T minus one another, we get 1 over T1 minus 1 over T2. Okay? Now, you can memorize this equation, or you can deduce or derive it by yourself. Okay? So, you notice that we can simply plug in the T1, T2, K1, K2, and then we can type the calculator, and then we get the EA. Right? And after we get the EA, then we can plug the EA back to one of these 2 equations, and then you can get A. Alright? So this is how it works. Now down here we have a practice question. You can pause the video and try it yourself. Now let's check. Here, of course, you can directly use this equation. Okay? So
natural log K2 is 23, K1 is 1.3 equals to EA over R. R is 8.31. Okay? 1 over T1 is 700 minus 800. Okay? Then we can proceed to our calculation. So we have natural log 23 divided by 1.3. We have 2.873 on the left. And here, 1 over 700 minus 1 over 800. And then you can divide it by 8.31. And we have 2.14887 multiplied by 10 divided by 5. EA. So EA equals to 2.873 divided by this number divided by 1000. And we have 134
kilojoule per mole. Okay? Okay, so that's it for the video.